Okay, you're welcome to this session on the platform on biogas technology. I am Jerome Mungwe, a researcher with the UNESCO Chair in Energy for Sustainable Development, the Department of Energy, Politecnico di Milano, and I'm also a lecturer at the School of Engineering, Catholic University of Cameroon in Bamenda. For this session, looking on the biogas technology, we will look at it in two parts. The first part will deal with the fundamentals of biogas technology, all that applies to biogas technology in general, large and small scale. And the second part will focus on the technology in developing countries. The first part, fundamentals of biogas technology. We know biogas technology is based on the anaerobic digestion process, which is simply the breakdown of organic matter in the absence of oxygen. This process takes place in four principal stages: the hydrolysis, where complex organic substrate like carbohydrate, proteins, and lipids are decomposed into simpler organic substrate like amino acid, sugars, and fatty acids. The second stage is the acetogenic stage, where these organic substrates are further decomposed into acetic acid or a group of volatile fatty acids, which include propanoic acid, butyric acid, and also hydrogen and carbon dioxide is produced at this stage. The third stage is the acetogenesis phase, or the dehydrogenation phase, where all the lower forms of organic acids are further broken down, mainly into acetic acid, hydrogen, and carbon dioxide, which are precursors for the biogas production. Then the last stage is the methanogenic phase, where the acetic acid, formic acid, hydrogen, and carbon dioxide are converted into biogas. From these four stages, we see that different groups of bacteria are involved. So it is a process that is coordinated by a consortium of bacteria. And each group of bacteria have different requirements in terms of the habitat. So when we look at the four different stages, the final product is biogas. Between the third and the fourth stage, the production can have two different pathways. One path where hydrogen and carbon dioxide is converted to biogas, and the other part where acetic acid is converted to biogas. The path that combines hydrogen and carbon dioxide is responsible for 30% of methane that is produced, while the path of breaking acetic acid to biogas is responsible for 70% of the gas that is produced. For the properties of biogas, first we recall that biogas is a renewable and clean fuel from the decomposition of organic matter with a calorific value that ranges between 21 and 37 megajoules per cubic meter. And this wide range is mainly because of the content of methane in the biogas, which ranges from 50 to 75% volume. The density of biogas is 1.1 kilogram per cubic meter. And it's a mixture, or when we talk of biogas, it's actually a mixture of methane, carbon dioxide, hydrogen sulfide, water vapor, and ammonia and carbon monoxide in various proportions. The composition depends on the type of substrate that is used and the digestion process, the condition of the digestion process, and also on the technical design of the digester. Various materials can be used for various organic material. I mean, can be used for the production of biogas, starting from food waste and organic waste from parks, gardens, organic waste and residue, and sludge from water treatment plants can also be used for biogas production, and most importantly, agricultural residues and manure. As earlier mentioned, within the environment where biogas is produced, there are some conditions that are necessary for the process. In anaerobic digestion, in the absence of oxygen, it is important that oxygen is not present in the digester. Otherwise, it will kill the methanogenic algae that are responsible for biogas production. However, there are some bacteria that can coexist with oxygen in the process. They are called facultative bacteria. This environment, the environmental conditions that are also necessary for biogas production is the aspect of temperature. We know already that the biological rate of reactions are a function of temperatures, and different microorganisms have different optimum temperatures for their operation. And above this optimum, the microorganisms may be inhibited or they may suffer irrevocable damage. So according to the temperature, the environment, we can have the process being described as a psychophilic process or mesophilic process or thermophilic process. Another very important environmental parameter is the acidity of the medium, which is measured in terms of the pH value. As you have seen, the first two stages of the process, the bacteria that are involved depend on acid for their survival, so they require an acid medium, which range between 5.2 and 6.3 pH. And the latter stages of the process, the bacteria require a much more neutral medium. In digesters where all the four stages takes place in the same container, a neutral medium is absolutely essential. The pH value is of very limited use in the control of biogas digesters, but however, in combination with other parameters, it could give some useful information. The microorganisms that are responsible for biogas process need macro and micronutrients and vitamins for their survival. So their rate of growth and activity is affected by the concentration of these nutrients. And the biogas production depends on the proportion of proteins, fats, and carbohydrates in the substrate. A balance is required, and this balance is largely determined by the carbon concentration and the nitrogen concentration in the substrate. If we have a high carbon concentration, it could lead to inadequate metabolism, that is less carbon dioxide is converted into methane, and a high concentration of nitrogen may lead to the formation of ammonia, which is inhibiting to the process. So therefore, we always have the ratio to measure the appropriateness of the nutrients in the substrate, which is called the CN ratio, which ranges between 10 to 30 is to 1. Carbon dioxide, carbon is to nitrogen. Then phosphorus and sulfur is also required by the microorganism, and a new parameter comes in, that is CNPS ratio, which range between the optimum is 600 is to 15 is to 5 is to 3. And the micronutrients are mainly metals like cobalt, selenium, molybdenum, manganese, iron, and magnesium. Concentration of micronutrients in a digester is a very crucial parameter that needs to be monitored. The recommended concentration, we have some that are given in the table that we have in front of us. For example, cobalt the recommended concentration of cobalt in your digester should be within 0.12 milligrams per liter. In the digester or in the process of anaerobic digestion, we can have inhibitors, which are substances under certain conditions can lower the process rate, or in toxic concentration can bring the process to a stop. These inhibitors can be introduced into the process via two principal ways. The first one is through the feeding of the digester. For example, you can feed your digester with dung from animals that have been taking antibiotics, so you end up introducing antibiotics into your digester, or from agricultural residue on which herbicides have been used, and you put into your biogas plant, so you introduce herbicides into the digester. The second way of introducing inhibitors into the process is through the intermediate products in the process. For example, fatty acid concentration between the first and the second stage. If the concentration of fatty acids is high, it could lead to process inhibition. Also, oxygen is an example of an inhibitor. So we have on the table here some inhibitory concentration. For example, if hydrogen, the concentration of hydrogen in the digester is greater than 0.1 milligram per liter, it can be a problem to your digester. And if the ammonia concentration or ammonia hydrogen concentration is greater than 3,500 milligrams per liter of free ammonia, that is in a pH of 7, it can cause problems to the digestion process. Now let's look at the operating parameters when we designed a biogas digester. For example, we need to have some parameters that we use to design the system. So one of the parameters is the organic loading rate and the hydraulic retention time. Usually in the design of digesters, economic consideration are not often the basis for the design and construction of a digester. The focus is not on maximizing gas yield or complete decomposition of organic matter that is introduced into the digester, but the aim is to optimize the degradation process at acceptable economic cost. So the organic loading rate simply is an indication of how much decomposable organic solid, which we call volatile solid, are introduced in the digester per digester volume per unit time. The second parameter is the hydraulic retention time, which is simply a ratio of the digester volume to the amount of feedstock that we introduce into the digester. Hydraulic retention time must be chosen so that constant replacement of the digester content does not flush out the microorganisms that are already existing in the digester. For example, we have the methanogenic algae that has a lifespan of 10 days. So if you do the design of your digester such that the hydraulic retention time is less than 5 days, you may end up flushing out these very useful microorganisms. So we have on the graph here the relationship between the hydraulic retention time and the organic loading rate. So if you increase the organic loading rate, you are reducing the retention time, so there is the risk of flushing out the microorganisms that are useful for the process. Another operating parameter is mixing or agitation of the digester content. Normally, when you have the content in the digester, because of density differences, we may end up having layers being formed inside the digester. The bulk of the bacteria mass collect at the bottom of the digester. Then the substrate may find themselves somewhere in the middle of the digester, and on the surface of the digester volume, we may have floating solids that form a scum. this can prevent the liberation of biogas, and also the separation of the bacteria and the substrate may lead to process inefficiency. Mixing provides intensive contact between the bacteria and the substrate so that the process can effectively take place, and mixing also helps to release the biogas that is produced. Mixing can be achieved in several ways, mainly mechanically using propellers and scrappers, and sometimes simply by the design of the digester, designing the components in a particular way can achieve mixing in the digester. The next aspect of the technology is performance parameters. After designing our digester or our system, we want to know which are the parameters we can use to follow up its performance. The very first parameter to measure is how much gas is produced per unit time. Then we may want to look at the biogas productivity or the production rate, that is how much gas is produced per unit time, per unit volume of digester. Then the next parameter is the specific productivity. In some literature they talk of the biomethane yield, which measures the amount of biogas that is produced per unit time, per unit organic material that is fed into the digester. Measuring the specific biogas productivity denotes the efficiency of biogas production from the loaded substrates. It gives us very little information as an individual parameter, but if we couple this with other parameters, it can make sense in determining the performance of the digester. Another useful parameter to measure the performance of the process or the digester is the degree of degradation of the organic matter that we feed into the digester, and this provides very useful information about the efficiency of converting the substrate into biogas. It may be determined on using several aspects of the organic matter that we put into the digester. That is, maybe in terms of the volatile solid, or in terms of chemical oxygen demand of the substrate, or in terms of the total solid that is fed into the digester. But often it is advised to use a volatile solid to determine the degradation efficiency. And this degradation efficiency is simply a ratio of the difference between the organic matter that went in and the organic matter that came out in a percentage. Now let's look at the classifying the process. As we already mentioned, the process is temperature dependent. Therefore, we can classify the process based on the operating temperatures. Through this, we can have a cyclophilic process which operates within 20 degrees Celsius of temperatures, a mesophilic process which operates between 20 and 45 degrees Celsius of temperatures, and the thermophilic range. In the graph, we have these operating temperatures, and we can see from the graph that, for example, the mesophilic process, the optimum is between 30 and 40 degrees. We can also classify the process in terms of the solid content of the digester, or the solid content of what we feed into the digester. So we can have either a dry anaerobic digestion or a wet anaerobic digestion. In a dry anaerobic digestion, the feedstock, the total solid in the feedstock is greater than 20%, and in the wet digestion process, the total solid in the feedstock is less than 10%. Wet digesters and the dry anaerobic digestion is favorable for thermophilic conditions, and usually have retention time from 9 to 45 days. And in the wet process, the favorable conditions are the mesophilic range, with the retention time usually between 60 and 95 days. We can also we can now look at the classification of digesters. We've just looked at classification of the process. We can look at classification of digesters. We can classify digesters in terms of the configuration of the digester. By configuration, we can have either the digester is a stir tank digester or completely mixed, which means the fresh feedstock mixes with what was already in the digester content. This type of design can either be periodically stirred tank or it is continuously stirred. Because of its operating constraints, the total solid in the digester is should be less than 10%. This type of designs are usually meant for thermophilic range of temperatures. Then we can have the plug flow or cross flow design, wherein the feedstock that comes in pushes out the feedstock, the content of the digester without mixing completely. It simply has an interface between the incoming feedstock and the outgoing feedstock. So the incoming feedstock does not mix with what was already inside the digester. Such designs also can function at a lower, slightly higher total solid as compared to the completely stirred tanks, and they also operate at mesophilic range of temperatures. Then we can also look at the digesters as leaching bed reactors or leaching bed digesters. This type of digesters operate at high, they can operate at very high solid content of the feedstock, greater than 15%, and they can either be mesophilic or thermophilic. The strategy here is we have the feedstock that is in a volume, and water is allowed to leach through the feedstock, which then decomposes to produce biogas. Then the leachate, or the water that has just gone through the feedstock, is what we call leachate. It can be used can be recirculated because it contains useful substrate that can produce biogas. Other types of digester designs include the upflow anaerobic sludge blanket design, lagoon digesters, and temperature phase digesters. We can also look at digesters from total solid content. We have here some pictures of digesters, wet digesters, which include the lagoon digesters, the upflow anaerobic sludge blanket digesters, the tubular digesters, popular tubular digesters, the fixed dome digesters, and the floating drum. They are all wet. They operate on the wet anaerobic digestion principle. We can also classify digester in terms of the feeding mode. Here we have the batch type, where the feeding is done once, and then the feedstock is allowed to decompose to an extent, and then the digester is completely emptied and refed again. Such designed meant for favorable for thermophilic range operation. Then we can have continuously fed digesters, which means the feedstock will be much more in a fluid form. So the total solid concentration is less than 15. Or we can have semi-continuously fed digesters where the feeding is not continuous but intermittent. We can also look at digester from the perspective of the strategy of growth of microorganisms. We can have suspended growth, where the microorganism population is embedded in the biomass, completely mixed with the biomass, and it's the simplest growth strategy. No special accommodation are required for the growth of the microorganism. The population of the microorganism in the digester with this strategy varies with time. So it takes some time for the microorganisms to grow. Most of the digesters that we have in practice operate on this strategy of microorganism growth. And we have fixed film growth strategy, where the microorganism grow on a surface called a biofilm. And the biofilm can simply be a material on which insertions have been made such that the biomass flow through it, and then the microorganism grow on this porous material. In this type of growth strategy, the population of the microorganism is kept at an optimal level, so it doesn't take a lot of time for the bacteria or for the microorganisms to grow. And because of this type of designs of the digester that operate in this mode have a greater output. For applications of biogas technology, I would like to mention here that the biogas technology is a very versatile technology which produces biogas that can have several applications. For example, the biogas can be burnt directly to produce heat for cooking or for warming of water. The biogas can be used to run stationary engines to produce heat and power. The biogas can also be used to upgrade fuel in vehicles for transport. Of course, the slurry that comes out of the biogas plant is very good soil conditioner, so can be used as fertilizers. Now we are through with basically through with the first part of our presentation. Just to recall that from the classification of the biogas process, we can have based on the dry matter content of the substrate that we use, we can have the process either as a wet process or a dry process. Based on the type of feedstock, the feedstock feeding mode that is used, we can have batch system, quasi-continuous system, or continuously fed system. And based on the number of phases, we can have a single phase system or a multiple phase system. And based on temperatures, we can have cyclophilic, mesophilic, or thermophilic anaerobic digestion process and corresponding digester design.